In this video, we're going to discuss about the most probable mechanism of oxidative addition reactions. Okay, so let us consider a simple general reaction, which is actually we have already discussed about this one. Okay, so here the organometallic complex, and this one is your the molecules which will going to form bonds with that metals. Okay, there will be two groups are there, so that two groups will going to form two bonds with that metal, no? So here, let's suppose this is your oxidative addition reaction. So when they the molecules or the groups will going to form that bonds with that metal, then it will going to give you a complex like this one, no? Having oxidation number what more, if this one is +1, then this will become what, +3. Okay, and the reversible reaction would be what, reductive elimination reactions. We have already discussed about this one in the previous video. Okay, so here the mechanism or most probable mechanism of these reactions or oxidative addition reactions, let's suppose the form only for the oxidative addition reaction, only oxidative addition reaction, that means only the forward reaction. Okay, we are talking about only the forward reaction in this part. Okay, let's suppose in case of the only the forward reaction, that means the oxidative addition reaction, the mechanism is depends upon the nature of this X and Y. Okay, so the mechanism of this type of reaction, is what, the oxidative addition reaction. Okay, this type of reactions that is only oxidative addition, not reductive elimination. Okay, we are only talking about oxidative addition. Okay, that is oxidative addition. Mechanism of this type of reaction is depend on what, the nature of X, Y. Okay, so if the nature of this one is polar, so the mechanism of this reaction will be different. Or if the nature of this one is non-polar, then also it will going to follow a different path. Okay, so let us discuss about this mechanism. So first of all, let us consider that this XY is your non-polar. Okay, non-polar. So as for examples, non-polar, that means they don't have any dipole moment, no? And overall dipole moment is 0. That means, let's suppose a hydrogen, so the overall dipole moment is 0 in case of hydrogen. So let's suppose that XY is hydrogen. Here X and Y are actually same, no? So or oxygen. Okay, so let's just discuss about the first mechanisms in which the nature of XY is non-polar. Okay, now let us consider or let us discuss about the most probable mechanism for non-polar XY. Okay, so here hydrogen is an example, no? So when hydrogen will going to react with the Vasquez complex, so Vasquez complex is this one, no? Iridium Cl, here L, and here L. Here L is represent what? L represent P is 3 PPSC, that means diphenyl phosphate. Okay, so when the hydrogen will going to react with this one, then they will going to they will going to, this reaction will going to follow a concerted step. That means the bond formation and bond breaking of the bonds and the formation of the bonds will going to occur at the same time. That means simultaneously. Okay, so here actually the bone, this bond will going to break. Okay, so this actually this is hydrogen, na? Hydrogen one bond, na? So this bond will going to break, and simultaneously two new bond will going to form with that metal. Okay, so here the ligands Cl and CO. Okay, so actually this is known as the transition state. Okay, so this transition state is what? This transition state is actually your three-center transition state. Okay, and the three-center transition state actually the existence of this three-center transition state provides the strong support for the concerted reaction mechanism. So the reaction mechanism is what? Concerted steps. Okay, concerted reaction mechanism. So that means the most probable reactions for non-polar xy will going to exhibit concerted reaction mechanism, and this is the transition state na. So and we know the transition states are not stable na, they will going to form a stable compound. Okay, so the next step is that this bond will going to break na, so this bond will going to break and these two bond will going to form. So that means the iridium will going to form these two new bonds. Okay, these two new bonds, and this bond will going to break na, so this bond will going to break. So CO, Cl and L. So from this mechanism, or from these steps, two steps, we are able to understand that the reaction will follow what mechanism? The concerted reaction mechanism. Okay, similarly, if you take another example of oxygen is also what? This is also a non-polar non-polar molecule. Okay, non-polar molecule. So it is the another example. Okay, so here if you observe the reaction between the oxygen and the viscous complex. Okay, so what will going to happen? But here the thing is that this oxygen bond, double bond would actually the bond between the oxygen and two oxygen atom will not going to break completely. Okay, so like this one, if you see the CO, L, here L and here Cl. Okay, so L represent triphenyl phosphine. Okay, here oxygen, and the final product will be like this: L, L, Cl, and here CO, oxygen. So this is the final product. But the thing is that the oxygen, we know that oxygen has double bond, no? Okay, so actually if you notice this one, let's suppose this is, so it will be slightly difficult for you, no? This one, this representation. So let's suppose this one. Okay, the orientation is like this one. Okay, so this is iridium. So what will going to happen? These two new bond will going to form. Okay, so one bond will going to break in between these two. There are two bonds, the two double, actually one double bonds is there. So uh, amongst these two bond, or between these two bonds, one bond will going to break. Okay, and two bond will going to form. So it will going to, actually if you that means only one bond will going to break. That means here like this one, it will going to give what type of bond? Like this type of bond. So here L, L, Cl, Co, L, L, Cl, and C. Okay, understand? But the thing is that if you if you characterize, or if you if you characterize this complex by using some characterization tools like XRD or any structural analytical techniques, then you'll find that the bond length of this one is similar to the single bonds, which which indicates that which indicates the the that these two bonds will not no longer double bond. No? This will not going to in the form of double bond in the new complex. It will going to be like a single bond. Okay, that means that bond length will going to increase. Okay, understand? So the bond order of oxygen is reduced from 2 to what, 1. Understand? So this is actually these are actually the two example of your what the first case in which the xy is what, xy is non-polar. So always remember that if the xy is non-polar, okay, then the reaction mechanism will be what, the reaction mechanism will be your concerted reaction mechanism. That means the bond formation and the bond making process will be occur at same time. That means simultaneous process. Okay, understand? Now the second the reaction mechanism, which is actually if the xy is polar in nature. Okay, so mainly if the xy is actually electrophilic polar. Okay, electrophilic polar. electrophilic polar. So electrophilic means there must be some, you know, electron deficient center, okay, in that xy, in this group, xy group, okay. So as for example, we can take CSTI, okay. So here in this case, actually in such groups or such molecule, actually the reaction will going to follow mainly, you know, concerted state SN2 reactions mechanism, or maybe sometime, you know, radical mechanisms. So that means if the XY is a electrophilic polar molecule, okay, then there are two possibilities of the most probable mechanism, okay. The first possibility is, let's suppose A, that it may follow SN2 reaction mechanism, okay. SN2 reaction mechanism, in which excuse me, in which two electron transfer will going to occur, okay. So two electrons transfer will going to occur. That means the two electron will transfer from metal to the ligand, okay. So the mechanism will be like this one, okay. So let us suppose we have an organometallic complex like this one, okay. Here M, L, N. So M represent, obviously M is the metal and L is the ligand, okay. And N, small n represent the number of ligand associated with that that metal. So here, and also the condition is that there must be two electrons. That means one lone pair must be there in that electrons, okay. Oh, sorry, in that metal. So let's suppose we have the CS3I, which is your what? Electrophilic polar molecules. Why this is electrophilic polar molecule? So if you draw the molecule of this molecule CS3I, okay, methyl iodide. So then it will be here you see, we know that the electronegativity difference of the carbon hydrogen is almost zero, no? Because the electronegativity of hydrogen is considered as what, almost similar to that of carbon, okay. So here in this four bond, among this four bond, only this bond, that means carbon and this iodine, they have some polarity, okay, polar nature. Why? Because in that iodine has more electronegativity than carbon. So that's why this electron pair, that means this pair which is used to form this covalent bond, no? This will going to shift towards the iodide, okay, iodine. So as a result, this center, this carbon center will become electron deficient center, okay. So electron deficient center means it will act as a what? Electrophilic, okay. And here this part will become del negative and this is become del positive, okay. So we have an electron deficient center. That means what? We have electrophilic polar, and this is the polar nature, electrophilic polar XY. So now coming to the that mechanism. So what is going to happen? You see here we have that metal, and in that metal one lone pair is there, and this lone pair can be donated to the your what? This is your that XY group, okay. So in this actually mechanism, let's suppose this is your ln m, and we again we actually we know that in this reaction actually follow what part, which part? Actually SN two part. That means substitution and nucleophilic bimolecular reaction. That means the bone breaking and bone formation will again going to be occur at the same time, no? That means that simultaneously the bone will going to break and bone will going to form, okay. So that means this let's suppose this is C and this is your H, this is H and this is H. So this is your like this, okay, and this is your excuse me I. So these two electrons will going to attack this electron deficient carbon center. Okay, so they will going to form a bond. When this bond will going to form, at the same time this bond will going to break. Okay, so this is the transition state. Okay, this is the transition state of this reaction, SN2 reactions. Okay, and this rate, actually the rate of this reaction is depends upon this transition state, na? So that's why it is actually bimolecular. Okay, SN2 substitute nucleophilic bimolecular. Okay, so again you see here this bond will going to break. So once this bond will going to break, then we will have this molecule. Okay, so this actually complex CH3. Okay, L N and here I. So I will going to this bond will going to break out. Okay, now the thing is that again here the metal and this iodine, they can form the bond, the second bond. Okay, this is the first bond, and the second bond actually going to form between the metal and iodine. Okay, so this is the final product. Okay, understand? So this product, actually this reaction follow what? Follow your SN2 mechanism. Okay, the second possible mechanism of this reaction, that means the reaction between the organometallic compound, that Pascal's complex, and which the polar molecules such as CH3I, is via radical mechanism. And in this reactions actually one electron transfer actually is observed. Okay, so we can take the same example. Okay, let's suppose LNM plus CH3I here, but the thing is that in these reactions, instead of that SN2 reaction, there will be some radical mechanism will be observed, no? So for that, what we need some radicals. So for that actually we have to apply some some radiations or some heat. Okay, such that we can get some free radicals. Okay, so for that, let's suppose by applying sufficient amount of energy, we can get the radical. Okay, so then this will be like this one, no? So CH3 radical plus I radical. So when we from CH3I, we can get this one by applying some amount of proper energy, proper form of energy, or maybe some radiations or maybe some heat. Okay, so we can get this one. Clear? So now the thing is that now the this radical, and here also first of all this LNM, this LNM will going to react with this radical. Okay, and if it will going to react with radical, then it will going to become a radical. Okay, so it will become like M radical. Okay, so this again there will be what? CH3 radical. Okay, CH3 radical, and finally these two radical will going to combine with each other, and the process is what? Only one electron transfer process, now this steps is one electron transfer process. So one electron is coming from this one and one electron is coming from this one. Okay, so the finally two bonds, that is metal CH3I, that means the metal will going to form two bonds, one with this one and other with this one. Okay, so this is the other way or other possible way of the reaction. Okay, these reactions. So hope you understand these two mechanisms. So mainly first mechanism is what? First mechanism is actually all the reactions, oxidative addition reaction is depends upon what? Oxidative addition reaction is depends upon mainly the nature of the XY. Okay, the group XY. So if it is non-polar, then it will going to follow the concerted state mechanism. Okay, so in which we actually observed that three centered transition state is there, no? So and here, but in this case, if xy is polar, then in this case the mechanism may be two types. Okay, the most probable mechanism, it may be your SN2 mechanism, or it may be your one electron transfer radical mechanism. Okay, understand? So we all have gain some idea about the factors which determine the tendency for a complex to undergo oxidation addition. That means whether it organometallic complex will going to exhibit the oxidative addition or reduction reactions. It depends upon what some factors. Okay, so we have some idea, no? So the first factor is, we already know that the complex must have what, some vacant site. So first condition is that it must have some vacant site, na? Vacant coordinate coordination site. Okay, so we understand this point, na? Because if there is no any vacant site, then how can the group will going to form bond with that metal? Okay, so it is the prime requirement for this oxidative addition reaction. Okay, but additionally there are some additional uh, conditions. So we already have some idea about the additional conditions. Actually, the first one is, actually we know that the stability of the actually complex. Okay, so if the products and the reactants. So let's suppose we know that first of all, we are actually taking what, the organometallic complex which have the coordination number 4, na? So like this ml4. Okay, like the viscous complex, na, IR COCl and two that ligand which L represent what, this one, na, IR COCl and PPS3, like the PPS3 and this 2. So there are total how many numbers of coordination? The coordination number is 4, no? So we are basically taking this type of compound. Okay, so they will going to give they will going to react with some group or some molecules like XY, and they will going to give you Ml4 or Ml plus XY, like this, na? So this is your what, 6 coordinate complex, or sometime maybe 5 complex coordinate complex may be also given by this one. Okay, so this is basically, if you see that the oxidation state of this complex is like actually D8, and this will go to that D6. Okay, by losing 2 electrons. Okay, then the oxidation number will going to increase, now then it will basically it is D8 and this is D6. Okay, basically, usually. Okay, so the second point is that so we have to actually the whether the oxidative addition will going to occur or not, it will actually depend also upon the stability of these two. If the stability of this one is better than this one, then we can say that yes, the reaction may be possible. Okay, and number third is your the bond strength. Okay, so let's suppose, so here let's suppose here, if you consider this same reaction, let's suppose this same reaction. Okay, ml4, here you see the new, how many new bonds are from X and Y, na? And here XY. So here in this reaction, actually this bond is going to break, na? Okay, and these two new bond are going to form. So we have to also consider about the relative strength of this bond. Okay, so if the bond strength of these two are better than this this bone, that means the strength of this bone, then it will give a good product. Okay, that means stable product. Okay, so we have to actually consider about mainly the main thing is that we have to also have some idea about the stability of the complex. Okay, stability of the product after after the oxidative addition reactions. Okay, so the product which is obtained from that oxidative addition reactions. Okay, so these are mainly the the factors which will going to determine whether an oxidative reaction is going to exhibited by that organometallic complex or not. Okay, so additionally again there are some more points are there. So from these studies we have also understood that the here we observe that the electron is actually donated from the metal, na? So if the electron will going to donate it from the metal to that group. Okay, so that means the metal should have what, so they have the capacity, or they can easily give, they can easily give the two electrons to the group, no? Okay, so for that, what is important for giving the two electrons from that excuse me, from that metal, the metal should be low valent, okay, low valent metals, and the oxidation number of the metal should be low. Okay, so we already discussed this one. Okay, so we can compare this one by using CO, cobalt, okay, titanium 1, yeah, 1. So the actually the possibility of the you know the uh, actually iridium can have more possibility to show this oxidative addition reactions. Okay, so because this can the electron can be easily donated by iridium, or the tendency of the donation of the electron is higher in case of iridium than this two. Okay, similarly we can also compare this. Okay, this is in group, okay, same in a same group, and this is in one period. Okay, so in case of this one, so iridium, so here, but here you see the platinum has oxidation number 2, and this one 1, and this one 0. So if you compare these three, then this osmium has more possibility to show the oxidative addition reaction, because the oxidation is number is 0 here. Okay, oxidation state is OS 0. Okay, understand, no? So this is the actually these are the factors which will going to determine the whether the complex will going to exhibit the oxidative reaction or oxidative addition reaction or not. Okay, so from the above discussions, we are able to understand that hydrogen can have the ability to show that oxidative addition reaction with some organometallic complex which can follow the factors like vacant site. If they have some vacant site, then they can react with excuse me, hydrogen. Okay, so that means it's okay. So we know that carbon has the similar electronegativity like hydrogen. So the electronegativity of carbon is almost same with hydrogen. So that means this carbon and hydrogen bond has also, they can also show the oxidative addition reaction. Okay, and even carbon carbon bond. Okay, so there are some examples, okay, which actually are intramolecular reactions. So let's suppose this reaction. Okay, PH3 PPH3, that means diphenylphosphine 3 iridium chloride. Okay, so here 3 diphenylphosphine and chloride is are there in with that iridium. Okay, so actually what will going to happen, since this carbon and hydrogen actually this hydrogen can also, this bond can also participate in the oxidative addition reaction, then we can say that the pH 3 P 2, let's suppose here 3, no, so one of them will going to react. Okay, so let's suppose this is Cl iridium, so one of them, let's suppose this one is P and PH2. Okay, and the other will be like this one. Okay, phenyl group, here this is the phenyl group. Okay, but here that means there are total three phenyl groups, na? So there are two phenyl groups, these two, and the another one is this one. Okay, so we know that there will be some hydrogen. Okay, there will be some hydrogen, and that hydrogen will actually going to react with this one. Okay, react with this hydrogen, this carbon and hydrogen can participate to form or to give the oxidative addition. Actually this one is like that. Okay, so just consider this one. Okay, so it will be like iridium. Okay, so this is your PH2, and here it will be like this. Okay, this is your hydrogen, no? So what will going to happen, this will going to break. Okay, this bond will going to break, that means this XY, it will be like this is your X and this one is your Y, that means XY. Okay, and this bond will going to break and it will form X and Y, na? So here let's suppose X is hydrogen. Okay, so that means in this case this will be like this one, na? PPH2, this is your group, na? So here let's suppose the Y group is this part. Okay, the benzene part, so benzene will going to form bond with that iridium, na? Iridium, so it will going to form that bond, and this bond will going to break, that means this bond will going to break, and the hydrogen is like X na, so it will going to form that bond. So it is like oxidative addition reactions, understand? So this is actually intramolecular part. Okay, so this is an example of oxidative addition reaction, which even we can see or which even uh, observed in intramolecular part. Okay, now coming to a very interesting point, which is actually known as ego-site, AGO-E-G-O-S-I-T. Okay, ego-site actually. Uh, uh, we know that that the carbon and hydrogen. Okay, this hydrogen can be this bond can be participated in that oxidative addition reaction. So here in this molecule actually, okay, in this molecule actually, this hydrogen can actually even donate one electron to this center, and here this hydrogen can donate one electron to this center. Okay, or this bond actually, OS, hydrogen and OS, this bond is actually three center two electron types of bond, and this type of structure, or this type of this type of bond, actually this bonding is this two no, three center two electrons bond is actually termed as ego-site. Okay, actually it is actually previously used to explain the covalent interaction between the carbon hydrogen group and transition metal center. That means carbon hydrogen group with transition metal center, but here even we can use the metal, hydrogen and metal. Okay, so previously it was used to a carbon, hydrogen and metal center. Okay, the three centered two electron bond, and this is actually previously known as ego-site. Okay, ego-site, this center or this bond, this type of bond is known as ego-site. Okay, so before going to discuss about the stability of the some complexes by using this ego-site concept, so we have to see some here you see this one is one-headed arrow. No? This actually indicate that one electron is donated from that hydrogen. Okay, but here to donate this electron to that metal, the metal must have some vacant site also. Okay, it is, please remember this point. But here let's go to this point. Here this we have some complex. Okay, iron complex. Here if you calculate this is the complex. Okay, and the structure of this complex is like this one. So if you try to calculate the the number of electrons out, you will not going to get the 18 electrons. Okay, that means outermost electrons, by using the oxidation method, or you can use even the normal natural, okay, neutral atom method. Okay, so you will not going to get the 18 electrons. Okay, if you don't consider the ego-site concept. Okay, but here the thing is that here you see this is the three electrons, and this actually this ligand represent this ligand. Okay, three this three represent the haplicity 3, that means three center. Okay, that means three electrons are donated from this ligand to that metal. Okay, but the thing is that the most important thing is that in this case, okay, there will be this this here PO methyl group. Here this there are three OCH3 groups are there, no? And here among this one and this one actually two, one from here, maybe one from here. Okay, hydrogen carbon hydrogen bond in carbon hydrogen bond, the hydrogen will going to donate one electron to the metal like this one. Okay, so if it will be like this one. Okay, so let's just concentrate on one part. Okay, it will be like iron what this is P it, this will be like P N O CH3 na? Okay, so this will be like O C H, and here some other will be there, no? O CH3 2. Okay, two remaining two. So this bond actually, okay, this hydrogen can actually even donate one electron to that iron, but the iron must have some vacant site. Okay, or vacant it should not be totally, the orbital should not be filled by electrons. Okay, some some orbital must be vacant. The meaning of this one is that. Okay, so similarly here you see this one, no? Let's suppose this one is remains in P, because here if you calculate the electrons, then it will going to give you 16 electrons. Okay, so we need extra 2 electrons now, and these extra 2 electrons will come from one from this one and one from uh, this one of these two, one from one of these two, and one from, let's suppose, this one. Okay, so eventually they will going to give you the 18 electrons. That means the complex will going to be what, uh, stable. And if you use the characterization tool, then you able to find that there were two bonds, two carbon hydrogen bond. Let's suppose this carbon hydrogen bond is actually not actually, if you calculate the length of this carbon hydrogen bond, then you will going to find that the carbon hydrogen bond is slightly longer than usual carbon hydrogen bond. Okay. And also it is actually not broken. Okay, because if you calculate this bond, then it is not the bond like between this iron and hydrogen. This hydrogen is not similar to that iron hydrogen bond. Okay. Why? Because this bond is actually not usual iron hydrogen bond. Okay, that means there are this actually there are three centers are there. Okay, that means this hydrogen is shared between these two center, iron and carbon. So this is actually what, this is actually your ego side. Okay, this bond is actually termed as ego side bond. Okay, understand? And the last and the most important use of this oxidative addition reaction is actually by using that organometallic complexes, we can even functionalize, functionalized. Okay, we can functionalize the alkene. Okay, alkene, alkane, actually alkane. Okay, not alkene, alkane, because the alkane bonds are actually this one, CH bond. Let's suppose this is methane. Okay, or sometimes CH2, sorry, CH3 H is like this, ethane. Okay, so it is very hard to break this bond, or it is very hard to functionalize in alkene. The reason behind is that the hydrogen and carbon bonds, okay, these bonds are very strong. Okay, actually these are almost 400 kilojoule per mole. So we have to apply this amount of energy to break this bond. So it is very hard, okay, to break this bond. These bonds are very strong. But by using some organometallic complexes, we can even functionalize this type of alkane. So it is very important, because in petroleum industry we need some different type of alkanes, okay, to use them properly, okay, or to get energy uh, from them properly. Okay, so the actually here they gave an example actually how to get that different types, how to do the functionalization. So when we actually use some specific organometallic complex with that alkane, then what will going to happen, we'll get this type of you know C R, suppose this double bond. Okay, this hydrogen, and here one hydrogen, this, let's suppose this carbon and hydrogen, this hydrogen bond will going to break. Okay, and they will going to form, this carbon will going to form a bond, and this hydrogen will going to form a bond. That means what, that means this part will going to behave as what, this part will going to behave as, let's suppose, X, and this part will going to behave as a Y. Okay, understand? And this bond will going to break. Okay, this bond, that means your CC, this is your XY. Okay, so in oxidative addition reaction, we know that this XY bond will going to break, and this metal will going to form bond with this X, and this metal will going to form bond with Y. Okay, but here this is what, this is your non-polar. Okay, non-polar, because all the carbon and hydrogen bond is what, because the electronegativity of carbon is almost similar to the electronegativity of hydrogen. Okay, so there, this bond is non-polar, no? So if it is non-polar, then it will going to follow which mechanism, concerted state mechanism. Okay, so that means they will going to give a three-centered transition state. Okay, so let's suppose this is your three-centered transition state. That means here you see this part is your Y, this part is your X. Okay, so here this bond, that means this bond will going to break as simultaneously this, the bond between carbon and that metal will going to form, and also the uh, hydrogen and metal will going to form. That means this formation of bond and the breaking of this bond is simultaneous process. Okay, it will occur at the same time. So here, then after this one, this is your transition state. Okay, so after this one, what will get, this one will going to give you, let's suppose this may be any R or H. Okay, just leave it. Okay, like this. So it will going to give you this one. That means this two bond will going to form, and this bond will going to break. Okay, so if you further, if you add some reagent, okay, reagent, so reagent, proper reagent, sometimes it will be act as a some catalyst. Okay, so sometimes we use some catalyst to carry out this final step. Okay, so to get back this Ln and the proper hydrocarbon derivatives which we actually want. Okay, hydrocarbon derivative derivatives. Okay, so this is a very important reaction, okay, in petroleum industry. So that's why the organometallic complex are important. Okay, because petroleum industry is very important for us now, because from that we only get the oils, okay, by using which we can run any car, any industry, any, okay, we can get electricity. So it is very important, okay, basically. So that's why it is very important topic. Okay, one of the most important topic. So there are many examples are there actually. So if you go through the book, your book, he 641 page number, then you're going to get some example of this complexes by using which we can get the hydrocarbons, proper hydrocarbons. Okay, so you can go through that book. So I'm not going to the details of this part, because I think you can understand this part. Okay, the main thing is that we can use the organometallic compound and that organic, if the organometallic compound will going to follow that factors. Okay, that means if the organometallic compound has the the vacant side, if they have low oxidation state like that, there are some factors which by which must follow, must actually, which must have with this organometallic complex to exhibit that oxidative addition reaction. Okay, so here if the here alkane will going to act as a what, your non-polar molecules. Okay, so they will going to give the concerted step mechanism, and they from by using some proper reagent or some catalyst we can get desired hydrocarbon derivatives. Okay, understand? But usually we cannot get these types of we cannot actually functionalize this alkane easily, because the bond strength is very high. This is the most important point. Okay, understand? So in next class we're going to discuss about insertion and elimination reactions. Okay, so up to this your what oxidative addition is over. Okay.